pleasure to have Professor Sanmi Koyejo from Stanford here to give an IFML talk. He's been doing, very interesting work in core ML when I first knew him when he started. But nowadays, quite focused on the kind of evaluating, understanding, and making modern AI systems more trustworthy. And so we'll be talking about some of that today. So, Sanmi, thank you for coming, and hope you can go down.
Yeah, thanks for having me. It's real pleasure to be here. Beyond this, as some of you might know, I finished up my PhD here in Dr. Koyejo's group, and it's a real pleasure to come back and see some old friends, mentors, meet some new people. So it's been incredible to visit. So really happy to be here in this room. So I'm going to get started, but maybe I'll preface by saying this is a newish direction in the work that my group is doing. And I say this because every presenter will say this, but I'm the one that really means it. That I'm really looking for a conversation because I think new directions often need a bit of fleshing out and thinking through. So I'm going to pick some things, and feel free to. The presentation is set up so that you can interrupt me a bunch, and so feel free to do that. And again, I really do mean it, so please do that. I'm going to pick some directions and how I've been thinking about what it might mean to measure AI models tied to the impact that you're having, as many of you, I'm assuming if you're in this room, you've noticed. And so some of the gaps that we've seen, and I guess some early thoughts on how we think we can make things better. So evaluations have been around in the field forever. Tested my clicker and then decided. Okay, there we go. So there's a bit of I guess back and forth on exactly where eval started in what we might call modern AI machine learning, but arguably one version of it was Hingelman and Bell Labs, who was doing sort of punch cards for character recognition, and so one of the first versions of collecting a data set, sharing it widely, having this sort of perspective of many people evaluating on a shared task as a way to think about sort of what it is the field might be doing and what progress looks like. I think I don't say this lightly, but I actually do think that as a broad community, benchmarks have grown to play such a huge role in what it is we are doing. So how we measure progress in the field. In a way that I actually think, one perspective is that this is a strong bias, and so we sort of are blind to everything that doesn't look like a benchmark. Another perspective, and one that maybe I'll kind of engage with a bit, in some ways, it's a superpower of the community. Like, we have this hyper focus when someone decides on some measure that people engage enough with. This is a way to measure progress in some way. Everyone just like hyper focuses on that thing, and we try to hill climb on that measure and make things better. And so we always have these conversations about whether AI can do a certain thing, and then someone chooses a benchmark that formalizes that thing in some way, and then the whole field engages, or some fraction of the field engages in this, and then all of a sudden we're better at that thing that was thought to be hard to do and impossible a little while ago. And so in some ways, I think this is at least something that as a incentive in the field seems to play a big role. So one version of the story, David Patterson has a paper, which I think is a good read actually, talking about, so the title is For Better or Worse, Benchmark Shape a Field. He was talking about computing a bit more broadly, but I think the AI/ML field has really taken this, maybe not explicitly, so I don't know that people are thinking about this in this way, but I think in practice, we really do anchor a lot on benchmarks as a way to measure progress in the field. I think to this end, we've actually done a good job on a couple of directions tied to this. So one version is what is sometimes called internal statistical validity. So this is this question of evaluating some performance of a model, and then being in the same sort of domain, changing some particular details of this evaluation, and asking whether the qualitative and sometimes quantitative behavior of models stays the same after you change some aspects of the evaluation process. So this is important because statistics actually tells us that everything should break. So statisticians in the room, what I mean is, all the basics of what it means to do good statistical practice are actually pretty badly broken in AI evaluation practice. We double dip, we look at the same data set over and over again, like all the stuff that would make statisticians, if you know any statisticians, you know, they will have nightmares about many of these things. These are sort of the standard things in the field. Nevertheless, if you evaluate the evaluation, so this question of like, for instance, so this particular paper from Rectanol asked the question of the extent to which performance rankings across models seem stable when I sort of create a new, in this case, they create a new ImageNet, which is again, this large classification data set. And they found roughly the ranking was quite stable. So models that were thought to be better, remain better, models that were thought to be worse, remain worse, despite the fact that, you know, ImageNet is out there, at least the version that people train and do all this stuff with. There's in principle the opportunity to do a bunch of cheating. There's a bunch of stuff that you know, training on the data set to some extent probably happens, but the qualitative general signal seems to be remarkably stable actually, in a way that confounds what would have imagined. So there's a little bit of work trying to understand this. I don't think we have full understanding yet. I think there's a very interesting deep statistical questions and sort of why this works so well. But I think it's a fascinating observation. There's another version of a question, which again, to my view, works surprisingly well. So this is the question of, again, sometimes called external statistical validity. So what I do here is I actually change, I intentionally change quite a bit about the problem and the process and the data collection. There's a recent paper by a former student, Wally Saladin, who I think will apply here at some point. So you guys should hire him. Never he applies here. And Moritz Hart last year. So what they did was they very intentionally changed a bunch of things about the ImageNet data collection process. They called bit tongue in cheek, they called the new data set ImageNot. Instead of human labeling, they did some automated labeling stuff. They very intentionally sort of broke a bunch of the paradigms in what ImageNet. So you know, ImageNet was this somewhat carefully curated data set with human labeling and all that. And they did a bunch of other stuff. And they were asking, will the performance ranking for models? So which models are thought better or worse? Will they remain stable? And again, found quite stable rankings of models. So the models that thought were better, remain better, that were worse. So some version about the progress in the field and sort of mid to long term timescale. I'd argue, I mean, the evidence here is in this narrower sense of computer vision models, various kinds of deep learning models. But I'd suggest that there seems to be some stronger, deeper signal about, in practice, things, some parts of validation process working quite well. So an example in, say, modern LLM world of how we might build a benchmark is, say, the graduate level Google Proof Q&A data set. So some of you might be familiar. So this was a data set meant to evaluate how well language models did on specialist questions out of physics, chemistry, biology. So there are a bunch of steps. You can look at the original paper or look at our paper that I'll show in a second, that went through a process of curating the benchmark, a bunch of expert labels to ask whether these sort of correctly capture so what correct answers might be in this evaluation, a bunch of validation, so the check for missingness and wrong answers. And when they were done, they found that experts got in a sort of 65 to 74% accuracy. Non-experts who could use Google, it's the Google proof, were able to get somewhere in the 34% accuracy. And GPT-4, circa now almost 2 years ago, was in a sort of 39% accuracy, almost definitely. I haven't looked at the most recent numbers of most recent models, but almost definitely. Okay, yeah, so much better. I love the real time. I love it. Okay, so models have gotten better on this. So the point here is again, just to understand a bit, if you're not familiar with the data curation process for some of these things. And so from this data, one could imagine making a couple of inferences. So one inference you could make is that the model can answer graduate level Q&A questions in biology, chemistry, and physics. And another inference you can make, so I'm showing here work, it's hard to see, but maybe partially my fault. But anyways, from our colleagues, who are, I guess, doing a marketing blog post. But what you can't see here, but what you may be able to read in the claim is renaming GPQA graduate level reason. So these are very different claims. So one is a very particular claim around question answering and sciences. The other is a broader claim about what it might mean to reason at graduate level in the sciences. And what I might say, and maybe you believe me, you don't have to, but I'd argue that claim one is a lot more reasonable than claim two. So claim one being this model can answer, again, these particular questions. Claim two being an inference about graduate level reasoning and an implicit comparison to, say, human, you guys, or many of you guys in this one. And so the arguments that you might make is that claim one is more supported by the evidence that was collected from this benchmark than claim two. A bit of a simple statement, but I do want to needle on this for a little bit.
Sammy?
Yes.
So, I mean, given that we don't know what the models are trained on,
Yes.
how do you know that the questions that it solves in your validated set aren't in the training set?
It's a great question. So the arguments that that these folks would make is, at least for the early evaluation. So the question here is, there's a very, one of the potential vectors of performance improvement could be discontamination. So people essentially either intentionally or unintentionally trained on the data sets that you're using. And so this might be part of why you're getting performance improvement. We talked a bit about this today. I think there's some signal that some part of this is happening. I'll talk a bit about work thinking about what the steps are. For now, we'll close our eyes and ignore that part, but we'll come back to it in 10 minutes or so. But I think it's an important question. So again, this validity of the claim is also tied to potential contamination issues. Okay. So to this point, I think there's a bunch of work thinking about things like benchmark saturation, again, potentially tied to questions of contamination, but I think that currently has a bit less attention in the field. I think most of the attention and current practice, think of a benchmark, are tied to, maybe somewhat surprisingly, people have found bugs in many of our large websites. MLU, for instance, people have found sort of incorrect answers, such that, again, models get good at answering those things. I guess if they get good at answering those things, if those things are wrong, maybe it is contamination for the conversations that were fit in a certain way. Nevertheless, I think it's productive to try to fix that issue. And there's also a bunch of work around new benchmarks come out. We started with 34%. We end up in, in a year or two, 80-something%. What do you do about the saturation problem? I think these are productive directions, but I want to argue today about a different direction than either of these. Something that I think is valuable to think about. Okay. For that. Okay. Okay, this is fine. I was expecting more steps. Anyways, so I'll argue, actually, in terms of impacts, there are a few different directions that I suggest to me that we may be in a bit of a measurement crisis. So signals for me include a bunch of policy decisions are being made based on the results of benchmarks. Various kinds of jurisdictions, visibly the EUAI Act, which is the governance landscape around Europe, uses benchmarks to decide risk of models, so high risk, low risk models. Lots of high stakes kinds of deployments are built or decided based on benchmarks. So healthcare systems will often, at least the ones that are thinking about deploying AI models, will often anchor on benchmark results as a way to decide. As many of you might know, including as I hear, exciting work here, but there is a ton of investment that's happening, arguably tied to benchmark scores. So hundreds of billions of dollars now, where the story that's been told, or the motivation for some of this investment is tied to benchmarks. And I'd argue a lot of public sentiment and trust is shaped by what we say the models are able to do. And that's often anchored on benchmarks. So the argument I'll posit today is that at least one part of what I think I'm observing in the landscape is that benchmarks were designed really for internal research evaluation, arguably a lot of competitive dynamics within the field, but are now being used for high stakes societal decisions. And I'd argue we're not designed for this. And I think this is a gap. And I think, in addition to, again, some of the things that we're working on, I think this is an area that is somewhat underinvested. And so I'd like to sort of make an argument for thinking about what measurement looks like with high impact and how we can improve what the practice means. So to this end, I'll talk about 3 lines of work that my group has done recently, and maybe talk from those lines of work some ideas on how I think we can make something better, the implications for research governance and decision making. The first one is talk a bit about specifics on what you might call, or what folks in measurement science call validity. So I'll explain this if you haven't seen it. This looks a little bit different than sort of say what a statistician might mean with validity. So I'll try to sort of expand on this and posit this as a good language and framing for thinking through how we can better design measurement practices. And then I'll move a bit and talk about some sort of tool building work. So think about probabilistic models that we've been building that we think are a interesting path for trying to improve both inference and also just the practice of building and measurement. And now I'll talk a bit about, I think, an interesting behavior in the field. I may or may not get to the third, but I'm also happy to send paper, depending on all the questions you guys ask me. I'm waiting for all the questions to come. But again, I may talk for a minute about predictability kinds of things. So I think, to my view, some of this shows up in other places, but shows up in a special way, I think a special way, in the AI field of thinking about predictability of model interventions, so things like scale, compute, data, things like TML and stuff like that. So I'll maybe spend 2 minutes on that part of it. So that's sort of my rough agenda for the next half hour. Okay, so first, I'll talk a bit about validity. So the reason I think this is important is, in my experience, and I'd be curious if people's experiences are different here. But more and more, there's this conversation that's happening between technology builders and broader society about what it is we're building, as mentioned, and then what they mean in terms of sort of various kinds of decision making. And for better or worse, the way this conversation is often most productive is via quantification. So we give them numbers and say, here's a thing that this thing can do, and this quantification is sort of what leads to the conversation. So if you think of, say, policy making around, so to just completely shift the frame on healthcare and people thinking about risks of new medicine and vaccines. The language of that is some version of like population risk, and who might do well, and sort of adverse events and things like that. And arguably, as I've argued a few minutes ago, within the AI field, I think a version of this already happens, and I think is such an important part of this conversation that it plays such a big role. So the core argument here is, again, sort of measurement and quantification are pretty important. And I'll try to argue a bit about within measurement and quantification, being more specific about what it is you're measuring is important. Maybe say a bit what and how. So as mentioned, I think it's an important language for framing what we need from the measurement process. And also, when we get the results of the measurement process, critically engaging with interpretation. So I'm going to talk a bit about this first paper. It's currently living in a GitHub link on my large GitHub, but eventually we're aiming for maybe this week or next week to be on archive. And that's Wiley, by the way. He's visited here at some point, so, but one of the leads of this line of work. So the arguments here, or at least the framing here, learning from folks who think about measurement and science more broadly, is that evaluation should be designed to support a claim. And where this is special is shifting from evaluation in a sort of generic way to sort of evaluation in a particular way. So again, let me explain or expand on this a little bit. So the proposed process is that in order to interpret an evaluation, one useful way to think about it, and I'll explain this in a linear way. I think in science in general, the actual process is often not linear, but the linear version of this is I have some object of a claim. So something we care about, some constructive criterion, I'll explain those in a second. And then we specify what we want to say about this constructive criterion, and then we think about the evidence that we need, and then sort of collect appropriate evidence to be able to make those particular claims. So a bit of an aside first, I want to make some distinction. I'll spend a bit of time on this in a second, between two kinds of claims that we might want to make. So one is formally called a criterion. So criterions are directly observable properties of systems. So these are things like prediction accuracy, precision recall. In my GPQA example, this would be a claim about the accuracy of the model on the specified questions. Construct is an unobservable kind of claim. So this is something that you can't see, effectively some kind of latent variable, and you need to collect evidence in a different way. So you can come up with some kind of instrument to measure this sort of unobserved and arguably unobservable latent trick. And so I'll try to separate between those two, because I think it's a key distinction in how we frame questions we're asking. Now, I've described this as a linear process. I think in practice, and I think all of science, but clearly many of you have done stuff like this, it's often nonlinear. So you might start with some evaluation process and then try to reason back to like what claims are reasonable to make from this evaluation process. So the real world version of this can be quite messy and still like scientifically appropriate and correct. It'll be easier to discuss things in this linear way, so I'll just stick with this for this discussion. But this is not to say, it's not a normative, like this is the right way to go through this process. It's just this is the easiest way to discuss it in 5 minutes. Okay, so here are some scenarios that you might, claims that you might try to make based on, for instance, the GPQA data set. So first claim, as stated previously, is AI models can accurately, suppose you get, you have GPQA benchmark, and you want to make the claims, models can accurately answer graduate level specialized multiple choice questions in biology, physics, and chemistry. This would be a criterion. So this is again directly observable. Or you might be looking to make a claim, AI models can reason. This is a construct, this is not observable. Again, you think about the set of evidence you need to collect to be able to make a claim like this. And so in the paper, we spent a bunch of time thinking through what this process could look like in a way that's valuable within the AI field. But I'll just speed through the dimensions that we think are most important. So at the high level, the key idea is at its core, whether a claim is supported by evidence, we argue should rest on the proposed 5 pillars. And validity as a sort of idea is sort of measuring across these 5 pillars. And so this allows us to answer the question. So for instance, in this setting might be, how well does, say, the GPQA benchmark measure what it's intended to measure? And so the 5 pillars here are first content validity. So this asks the question whether the evaluation covers all the relevant cases. And so for claim 1, you might argue, I didn't state this in detail, many of you that know the benchmark might know that an expert curated, there's a sort of very careful evaluation of gaps between experts and non-experts. And so you could argue that claim 1 is well supported with the content validity. But you might argue that if you're interested in reasoning, perhaps content is insufficient, even at graduate level reasoning, because again, the claim being made here is much broader. So there's multiple choice, which is somewhat limiting, because it doesn't evaluate all the ways that we think graduate levels individuals should be able to reason about questions. And there's also a limit in terms of the kinds of disciplines that are covered. A second is criterion. So this is asking the extent to which, so one way to make strong claims about an evaluation process is to anchor this against sort of known facts that exist in the literature. I think for AI, this is new-ish. So I think we're still developing sort of established sort of known validated standards. But nevertheless, in scientific measurement more broadly, one way to be able to make this argument is tied to validated standards. So I think in the field, one common way people like to do this is tied to human evaluation of various kinds. So you might argue that claim 1 is well sort of validated because criterion is validated because we can tie this to human expert accuracy for these kinds of questions. Whereas maybe for reasoning, I think this might be a weaker claim. A third is construct validity. So this is asking the extent to which the measure, covers the thing that it's intended to cover. So I think one of the key ones, particularly for ideas that are unobservable. So, criterions, these are easy because the observable is the quantity, so there's none to do here. For constructs, again, there are lots of gaps. One easy one might be to, I think, the earlier conversation, memorization could be the answer, or the reason why we're getting difficult. So nothing so far separates memorization from reasoning. A fourth is external validity. So does it generalize across environments and settings? So for claim one, arguably reasonable. It mirrors the real world by construction, and so arguably well validated. And for claim two, I think much less so because again, much more limitation. Now, finally, one that I think is quite important and way under indexed on in the field is consequential validity. So what are the real world implications of the evaluation process and the implications or the sort of statements that are being made? So, I mean, one very clear the observation is that many stakeholders take what we say and then sort of push them much further than arguably we intend when we say them. So, for instance, stakeholders overgeneralize competence when we say models can do certain things, and so push it beyond, again, the narrow measurements that we've actually made. I think these are important, and we should be thinking more carefully about how to make careful, understandable statements that actually can be translated appropriately without missing some of the gaps. Okay, so that's sort of the core statement here. The key idea, I guess, what I'm trying to get at is, I mean, one part of this is bringing some of the language about measurement science into the field with the hope of giving us a way to think about some of these questions. Some of this is happening, I think, not enough, and so the pitch here is to think about this more. Additionally, in the paper, though I won't have time to do this here, talking through some of the process of how we can do this productively. So what do the actual steps look like for trying to engage in, again, having much more validated or valid measurement processes and practices within the AI field. So one key idea, do want to mention this because I think this is helpful, is for making progress in thinking through measurement science, one of the tools that folks who think about measurement use is what are called nomological networks. And so what this is connecting constructs to each other. So one of the ways that you can make claims about constructs is not just the construct in isolation, but actually how things connect across different constructs. These are generally designed for human kinds of constructs. I think there's an interesting argument of the extent that we can pull this into the ways that we're building sort of constructs for AI models. So these are things like, reasoning can be composed into a bunch of different kinds of reasoning, mathematical, common sense reasoning, logical. Often the gap across people when they're talking is that everyone says reasoning. People don't specify what they mean by reasoning. Someone's talking common sense, someone else is talking mathematical reasoning. They say, LLMs can reason, LLMs can reason, but they actually are saying completely different things. But have different mental models and not actually speaking the same language. So the call here is for more specificity and then actually working through some of the process. One more sort of process thing I'll mention is they're good tools for thinking about operationalizing this. So this very simple, at least one simple process argument that you could go through. So think through when coming up with either a new benchmark evaluation process or coming up with trying to come up with validated claims, how you might go through the steps of making sure that, again, you're making much more careful statements. So to summarize this first chunk, I've talked a little bit about validity and how the key argument I'm making is that it should be tied to specific claims. And there is a language that we can build that exists already that we can use. And the work that we've done is try to specify this for usefulness within AI practice. The things like content, criterion, construct, external and consequential validity as ways to formalize this process. Okay, so I'll shift gears now, unless there are any questions. I'll give half a second. Okay, so I'll shift gears and talk a bit about probabilistic model. So here again, the work I'll discuss borrows from measurement science field, where the work that they do is so thinking through how to disambiguate factors that explain measurement results. So one way that this can be helpful is for latent factors, being able to operationalize logical networks. And the key ideas here are generally probabilistic models, latent variable models. So they have names within the field. I'll talk about one called item response theory, but things like factor models show up a ton. One can easily build other kinds of probabilistic models to help explain and improve measurement practice. So this is work. There's an archive already and going through some review process with students and also some great colleagues. Okay, so when we're building evaluation processes for models, the thing we typically do, particularly in modern practice, is we average number of things, answer questions that a model gets correct. So bit tongue-in-cheek, within the measurement science world, this would be called classical test theory. I say this tongue-in-cheek because this is modern AI practice. But again, the argument here is folks that think about measurements have been doing stuff like this for a while and have shifted. And I'm going to pitch some of what they shifted to as maybe productive ways for us to improve what we're doing. So some of the gaps in classical test theory or averaging and ranking performance are that it requires all the questions to be perfectly overlapping. In particular, you generally get very unreliable results if your different models see different questions. This shows up a lot more in modern practice. So a couple of different ways. People that are doing agentic kinds of things, often the kinds of questions you're asking models are not the same across its sort of measurement process. Folks are doing red teaming. Again, the models aren't seeing the same exact questions when you're evaluating them. And what has been found, I'll give some examples here in a little bit, is that if I measure the models in sort of a different set of questions and I compare the responses, so I average performance for model A in question set 1 and model B in question set 2, comparing performances directly often actually doesn't give me any kind of reliable result. So that leads to a gap. And this is a gap, I argue, that comes from the process of using simple averaging and ranking. And so I'd argue for how to do some of this better. The other questions you might be interested in is not just predicting or sort of evaluating models on a fixed data set. So this is illustration of, in this case, HELM, the holistic evaluation of language models. Here it is a bunch of different data sets, a variety of different models evaluating a variety of different questions. But you might also be interested in how models do on sort of new generative models. And you might also be interested in sort of how models do on new data sets for existing many generative models. For those of you that have done recommendation systems kind of things, actually lots of ideas in that world show up here. So I think it's actually severally kind of interesting for those things to come back. Okay, so one simple model, and the one I'll go through in a few minutes, is what is called item response theory model. So very simple latent variable model. Your model for correctness of a model your model for correctness of a model, or say an LLM in this case. So how likely it is to get the answer right is decomposed into 2 latent variables. One that's called model capability, another one that's called question difficulty. And the intuition here is that if a model is highly capable and the question is very easy, then the model probability, so this number gets big, sigma gets something close to 1, so the probability that the model gets the question right is very big. If it's the other way around, so question is very difficult, model is less capable, you get 0, and then things are close, then close to 0.5, so coin flip, the model gets the answer right. Within the psychometric field, this is called the RASH model. This is arguably the simplest of the models in this family. You can do all the fun things you want to do to make this kind of model much more interesting. So this is, again, the basics of folks that think about measurement within mostly for human measurement, but it's one of the core models that they use. And so we looked at a variety of data sets from HELM, in this case, about 200,000 questions, evaluating about 172 language models, not full overlap between the models and the questions. And here we're just looking at correct or incorrect. So we're modeling this P of y equals 1. You can model much more interesting sort of kinds of response types. But for here and for this paper and this work, I'll just focus on correct or incorrect modeling. And so the first thing that we checked was, unfortunately, I think the presentation looks much worse. It doesn't look great on my slide, but it looks really, really bad here. But hopefully you get the gist of what I'm trying to show here. So the first thing that we show is just checking reasonableness. So are we getting good correlation if I look at the full data set, the results that I get from using the IRT model to rank which models are better or worse compared to the results I get from using the classical approach. And the main story here is sanity checking. So I want, if I get to see all the data, the new approach, or at least the argued new approach, should get me the same results as the old approach. And we show very strong correlations. So AUC, or essentially a 1 in the rankings of models. The next thing we test is this thing I mentioned briefly. So what happens when they're not perfect question overlaps? And so we picked a random subset of models and a random subset of questions to ask some of those models that were disjoints. And in the paper, we show in some detail that if the questions don't overlap, simply evaluating and averaging can actually lead to, or essentially chance comparisons between models. So in this case, we're getting an AUC 0.5. So sort of your accuracy in being able to predict which models are better or worse is about chance if the questions don't overlap perfectly. Yes.
Do you have test questions or test IJ pairs?
So I is model, J is
Right.
question.
Yeah, so the thing is, your model has a ZJ,
Mhm.
and so if I have a completely new question,
Yeah.
I don't know it's ZJ, so you don't have a model you don't have a prediction for that question anyway, so how do you test it?
Yeah, so for this work, I'll talk about, so this work we do on, we have a train set and then a separate test set. And so the test set is not overlapping, the train set is. I'll talk a little bit in the later path on how to get around the problem.
No.
But for here, the test set is this one.
Yeah, I mean, okay, so, I guess the question is it disjoint IJ pairs or just disjoint J's?
This
Is it a
is,
question I've never seen before, or is it a question model pair that I've never seen before, but I've seen the question before as well?
yeah. For the full evaluation, so I guess for the combined train and test set, you will have overlap and I or J. For the test set itself, you have completely disconnected pairs.
But then how do you know what your model predicts because you don't know the ZJ for that?
So because in training, there's overlap. So in training, I can fit the Z parameters. In test, there's no
I know
overlap.
it's a new question which you've never seen.
So I'll talk a bit about that in a second. Yeah. But for this experiment, we don't do that. I'll talk a bit about how you can do this for this cold start problem for those who recommend this. Good question. Okay. Second evaluation or second thing that we can do with this is do some basic active learning. So this is interesting because there's a bunch of evidence that perhaps our benchmarks are too big for at least what we're trying to measure. People have done sort of random subsampling of benchmarks and shown that you can get similar kinds of inferences for benchmarks using many fewer samples. We do a version of this. We're exploiting the probabilistic model that we built. In this case, we use a Fisher information-based sort of acquisition function, and we show that for some of the question sets, you can get, so the question sets here within Helm, there's a bunch of like different so Helm is a benchmark suite. It has a bunch of subcomponent benchmarks. And we show for some of the subcomponent benchmarks, which you can't read here, and I can sort of kind of read. They can reduce the number of samples you need by, in some cases, up to 80%, while still getting sort of high performance. So useful again for sort of reducing query costs, so how many samples you need. Finally, semi-finally, one other thing we do is we play with predicting question difficulty. So here the idea is I'm going to, so in the classic clarity, this cold start problem actually hurts you quite a bit. If I get a new question that I haven't seen before, how do I know sort of how difficult this question is? And so what's typically done is you essentially need to refit the whole model again, or both all the new data. In our setting, we use an EM kind of algorithm, so you might just continue the training to sort of fit new data. But an alternative and maybe more scalable approach, which we suggest in the paper, is to just build it as a predictive problem. So what we show is you can just sort of predict the difficulty based on existing items, predict the difficulty, this little variable for new items. And this procedure actually seems to be quite accurate and work quite well. And so we show some results here where we hide some new example, so unknown difficulty plus immediate questions, and we show quite good performance compared to knowing them in terms of predictability and then sort of ranking of performance. And finally, we play with this question of synthesizing questions that match a target difficulty. So now I'm going to tell you how difficulty here is modeled by this probabilistic model. I'm going to state the difficulty I want and ask, can I synthesize a question that is as difficult as I would like to target? And in the paper, we suggest that this seems feasible. Under the hood, we use a generative model to synthesize new questions. And in order to target difficulty, we use a combination of supervised fine tuning and PBO, which is targeting, essentially training the model to synthesize questions where, so what you want is synthesize a question such that if I evaluate difficulty, it matches the difficulty number that this all been chains together. I'm sure that you can do this reasonably well. Let me show some examples. Yeah.
So you said it's a model, the difficulty is modeled by a probabilistic model, and then you mentioned that it's under the hood, it's some generative model. So basically, are you generating and then asking the model to score the difficulty?
Yeah, so we have a difficulty scoring model, which is
that's a different model.
this guy, yeah.
So it's like a scalar which is close to a reward function because we mentioned something like PPO. So it's like a reward function given to measure the difficulty.
So the reward is how close is the difficulty of a synthesized question to the known or predicted difficulty based on our predictor.
I see. So I have a question like this. Let's say you have a model which is well trained. It is well known that it's well trained. Let's say some trillions of tokens from Llama, and you use the loss to measure the difficulty. So is it? Do you think
it's a good question? So the question is, are there other difficulty signals that I can use instead of? I've found loss to be quite unreliable as a measure of difficulty. Unreliable. I think partially because again, there's a bunch of. I mean, I don't know that this is a panacea, so I want to be careful about overclaiming here. But I guess our experimental results that suggest that both loss and also people play sometimes with. I mean, very close to loss would be, the gradient, the underlying probability for the last token or something. People play with these uncertainty measures. We found them pretty unreliable as a difficulty anchor for at least our analyses, but I think it's an interesting direction. We found a bit more success with explicit models.
Thank you.
Okay. Okay, so some examples and also showing sort of some results. And given this sort of amortized prediction kind of approach. Okay, so to summarize possibly the we'll see, maybe last section. So added response theory and sort of probabilistic models for evaluation processes, I think are a productive approach that I think I'd argue hasn't been done that much in the field. There's a lot of evidence that this can be useful coming from measurement science more broadly. And so a second pitch is maybe using some of these latent variable model, arguing that it can do some useful good things for helping us scale evaluation processes and measurements within the time. Okay.
Is it only a single dimensional difficulty model here?
In this case, it's univariate. As if well, you can make those more complicated. But in our work, so I should also say we evaluated some more sophisticated latent variable models. In this paper, we found better fits, but by very small margins. And so we find the sort of basic RAS model called a 1PL model good enough for at least what I showed today. So short answer is yes, long answer is yes, I guess, but longer, complicated one. Okay. I will skip the third part. I will mention on the side that I think an interesting set of questions that we often ask are to some extent, I mean, they're not completely unique to the AI field, but I think an interesting set of questions on predicting intervention effects. And I think there's a very productive science, if you like, in trying to understand. So there's work around scaling laws, around data and compute. We've done a bit of work in things like model collapse. So model collapse is this phenomenon of training models on synthesized data from previous model iterations and just doing this loop over and over again and asking whether or not models will sort of break if I do this for long enough. And the short answer is it's complicated. It's the short answer. And the longer answer is the few minutes that I'll skip here with some students doing some excellent work here. Okay, well, so let me talk for 2 minutes about some open problems, if it's okay. I think I'm right at time. Okay. So open problems, things I think could be productive and things I'd be excited for the field to spend a lot more time on. So one, I think we don't understand the links between upstream and downstream measurements. Upstream being what we think of as, for lack of a better word, cognitive capabilities of models. So I think there's a lot to do in sort of building additional benchmarks, thinking of ways to understand the extent to which in the measurement science field we call convergent and divergent ability, a bunch of work in sort of understanding latent constructs that underlie benchmark processes, better defining again what it is we're measuring upstream. And I think there's a complete dearth of signals on downstream. Downstream here meaning what people actually care about in practice. So if I'm evaluating a model for some real popular use case, we know very little in a quantifiable way about how well models will do. So a couple of steps here. I think there's a bunch of work in just building additional benchmarks for downstream. I think there's a bunch of work in connecting those back to upstream so we know how the capabilities of models tied to performance in a predictable way. And I think there's a bunch of work we do to both understand new capabilities and how they might affect downstream impacts, and then using downstream to inform what new things that we might be looking for upstream. So I think productive work there. Another open problem is most of our non-math and code relies very strongly on multiple choice question answering. This is nice because it scales, but as argued at the first part of this talk, I think it actually has lots of gaps in terms of real world usefulness. There's a bit of work in AI as a judge. I think it's promising, but some work suggesting, observably it's error prone, and there's some work suggesting, there's a recent paper by Hartz and Dorner, I don't know where it's talked about, but has some interesting things to say about, these arguments about how well we should expect AI as a judge to work. We're doing a bit of work through Zach and trying to think through some ideas from scalable oversight. So these are tools that come from mechanism design to come up with new ways of avoiding multiple choice as a way to evaluate open-ended question answering models. A lot of the tooling, including what I've talked about today, are very tied to what we think humans do, and then sort of imposing those, so anthropomizing, for lack of a better word. What models are doing should match what humans are doing. We don't know what breaks. We know that things are not robust. The ways models have high performance don't match the way humans have high performance. In particular, very simple things we talked today about. If I give models various kinds of math tests, for a human, you'd expect if a human can do a certain complicated math test, they can do that well, they should do sort of other math tests that are similar. Maybe the numbers are changed. As you might know, models break quite completely, actually. If the evaluation is the same, the numbers are changed, or the sort of setting is changed in small ways. We don't know, I mean, we sort of have hypotheses about why. I don't think we know that well. A lot of the tooling I've talked about strongly anchors on essentially variations on smoothness and generalization that come from human framings of measurement. So psychometrics is really about measuring human. I think we need more science and some of the ways models can be different so that we can refine some of these arguments. And finally, I think we have an institutional problem as well. So again, we want these evaluations. One of the tools, or one of the things that we like, that these evaluations say something about AI for the world. And I don't think we have good institutions for doing this. So questions about what capabilities actually matter, what kinds of risks deserve measurements, silo context, institutional structure, and lots of gaps there. There's a recent paper with some colleagues that we did, trying to talk through some institutional building that we think could help close some of those gaps. So if anyone's interested, you can look that up. So I guess some thoughts on how I think we can move forward. So I think for us, I'd imagine most people here are researchers. I think we should just be much more careful in what we're stating or claiming about what our evaluation processes are measuring. And some of the work I've suggested about using theory, some theory to help connect measurements and capabilities much more strongly. I hope the industry spends a bit more investment on evaluation infrastructure. Currently, there's a strong anchoring on leaderboards. I think a lot more that can be said and done, as I've argued. So hope that we can sort of engage in some of this. Spending a bit more time grounding capability claims in appropriate evidence. I think one of the ways that things might change is that policymakers and civil society might just ask more of us. And so I hope that some of this happens, where when we make claims, they ask us to actually be more specific and clear what claims we're making, as opposed to what happens now, which are, I think, very broad claims that are unspecified and that are vague. But also there's, I think, infrastructure building work here and like funding independent evaluation research. And I think there's a big role for civil society in helping us specify again what we'd like to do, so that we can do them better. Okay, so I'll stop here. Thank you for your time. I talked through a few different directions around some early work that we're excited about in my group. Hopefully some of this might resonate with you, and thinking through ways that I think the measurement practice within the field can be much better. I'll stop here, and I don't know if we have time for questions, but yeah, I'll stop here. Thank you.
Yeah.
This is more of a policy question. I mean, you mentioned independent evaluation. So I noticed, for example, OpenAI funds some of the work at Stare. I mean, given how much money, as you mentioned, is at stake, should academics who take money from companies that create or do tech in LLMs, like, should they recuse themselves from research on creating benchmarks in terms of financial conflict of interest?
Yeah, this is a great question. I think I've pointed one, so thank you. I guess individually, I hope that my interest in scientific practice is stronger than my willingness to, I guess, convert on my work to be aligned with what OpenAI wants. And I should also state formally that these are set up in such a way that, in particular, I think most institutions are very careful actually about industrial funding, at least visibly affecting the scientific process. So these are done in such a way that either gifts or some way that, at the surface anyway, they're not influencing. There's also, I think, very visible. This is a good question. I won't answer it, but I'll talk around it a bit. But one interesting version of this, right? So there's this. It wasn't ARC. It was another one. I don't know if this is what you were.
The AGI, ARC AGI.
Was it ARC AGI?
Frontier Math.
Oh, Epoch. Yeah, it might have been Frontier Math. Epoch, where OpenAI funded it, but also got early access to it. And
Frontier Math, they have it.
yeah, so this.
Eric and I have discussed.
I see. Yeah, no, I think these are very worrying. I think the other side of this, though, is these things are expensive. My group is expensive. In an ideal world, maybe I'd remove OpenAI from this list of funders. I think practically right now, probably no. I guess, personally, I think I'm doing reasonable things, but I think it's reasonable for the field to keep checking on it. One way to maybe improve this, I think, and academics think a lot more about the extent we can make practices open and sort of open source. We try to do this as much as we can. Almost everything I talked about today, including like the second thing is deploy this product home now, open source code and I think those are a bit of a, defense against some of these potential tensions. I don't think it's perfect. I think it's an important question. Right now, I do not, but I think it's an important question. And part of the norms that may develop is that if we're going to do evaluation and make strong, societally important claims, that things need to be separate a bit more. I think that might well be.
One of the things you mentioned was that one thing to do in previous slide, one thing to do for researchers is to report validated evidence and not just scores. What does that mean?
So what I would like is, I guess the aspirational version is that evaluation process results are anchored in validity practice. So you're making not just a score claim, but actually like a score result. We actually stating precisely what a claim you're looking to make and going through some of the process I showed in part one of like how this claim supports the evidence. The narrow version is a scientific argument. Scientific argument should also include good statistics, so this is the number, but also talk about my error bar, and some of that process, I think. We don't yet have the practice in there, I think improving that process would be useful. In many ways, I think this should just look like math, like science. So, in science, if you're gonna make a scientific claim, again, there's a lot more expected than a number. The arguments, the very like succinct version of this is that AI evaluation should look like science. So I don't know if that answers your question, but to the extent our caricature, what
Yeah,
scientific.
maybe if there was an example, but we can take it off.
Sure, so I don't know that there's a good visible example.
Yeah,
I think that's
then
part of
it, yeah, that would answer it in my mind.
Yeah, but here, again, okay, so no, to the extent that, again, make clear claims, the arguments are not, this benchmark says something. Or not only that, but if you're gonna use this to make an inference, make, tie your argument to that inference and then do some good statistics on that.
Right.
Yes,
If you want to sort of look at FDA like gold standards, then you need to state the hypothesis upfront before this study. You generate the study, generate the data.
Yeah.
And test the hypothesis, and you can never use the data again for anything else.
yeah, this is a
It needs to be
good
published
question.
before, and you should just bury everything, because
Yeah.
anything else is behind.
I'm mixed on that. So the beginning of the talk, if you remember, this is a good point. I think in standard practice again, for sure, this is what is happening. And statisticians tell us this is the right thing to do. I think the pushback a little bit is that we've completely broken that within the field.
Exactly, that's what I'm.
But I don't know that that breaking is the same as this breaking, I guess. This is my,
Isn't that
argument.
what your bullet is sort of saying? You
Uh,
state ahead of time what you want to test for,
yeah,
do everything and then throw everything out.
I think it would make it better. I'm making a different argument. Actually. So the argument I'm making is about the constructability process, not about purely the statistical argument. And I guess the counter to the statements that you're making is the observation that we've been terrible statisticians, but still get reliable signal. So I don't know the answer to your question, and maybe I'll even anchor more. There's a bunch of work in biomedicine, for instance, that has been talking through other ways to build scientific evaluation processes that don't do the sort of blinded thing. So there is observational causal stuff. There is like bandit kinds of work. So like, so I don't know that the end all answer is blinded register studies. I think it is helpful. It at very least makes you honest in a way that we don't have been honest before. It's a bit of a big hammer, I guess. Maybe if so is this the way to make things practical and scale? I don't know. I'm much more worried about the validity than maybe the practice in this way. But no, if things land there, I'd be perfectly happy.
All right, let's spend time.